We're now going to turn our attention to another important application of integration: density, mass, and center of mass. And the central question in this section is this. How do we deal with objects whose density is not constant? So how do we deal with objects whose density is not constant? And first of all, we should talk about what density even is. So density is how much mass is packed into a volume. So how much mass is packed into a volume. And one way we can think about this is, say you have a suitcase here, and this suitcase is packed with, all that it has in it is just a bunch of feathers. So feather after feather, and it's packed to the brim with these feathers. And you can imagine carrying this suitcase around, like maybe a long airport walk. It wouldn't be too bad. But say that we had the same suitcase, and instead of feathers, we're going to have just a bunch of rocks in there. And so same space, same size suitcase, but now we've got a bunch of rocks. And these rocks are pretty heavy. For sure, if you're walking through the airport, you want to be carrying this suitcase and not this one, because even though they're the same size, like the volume is the same, this one is a lot easier on you. So density is mass divided by volume. So density is mass divided by volume. And this is a relationship that is very central to everything that we're going to talk about in this section. Another way of thinking about it is mass is density times volume. So we'll use that as well, of course. So here in this suitcase, the density, maybe it's something like 50 grams per, I don't know, cubic foot. And here in this situation, the density would be something like maybe 12,000 grams per cubic foot. So units of density are going to be mass units over volume units, always mass units over volume units. And this relationship between density and mass is going to become important because we're going to start talking about situations where, here the density is just constant throughout that suitcase, we're kind of assuming, and here the density is constant. But we're going to look at situations where density varies, and it varies continuously in a certain situation. And we want to be able to, answer questions about, well, if the density varies, how does that affect, is it still possible to find the mass of this in this situation? So in our first example, there's a road that goes away from a certain intersection in a city center. So there's a city center intersection, and then there's a long road. And cars are piled up on this road. A whole stream of cars. And we want to think about how the cars are distributed along this road. So the city center is where it's going to be the busiest because a lot of things are happening right at this intersection. But as you get further and further out of town, there's going to be a lot of cars right in here, and then fewer cars as you go further along the road. So this is an example where the distribution is not constant on this road. It's sort of concentrated in here, and then it gets more sparse as we travel out. But it is known that this formula, C of x equals 200 plus 100 e to the negative 0.1x, this models the density of the cars per mile. Oops. And we'll say like X miles east of a city interchange. And so maybe a question that we would want to be able to ask is, how many cars are there in the first 5 miles? And meaning the first 5 miles east of that interchange. So we don't have a function that tells us the number of cars. All we have is a function that models the density of cars. So this is a density function here. And yet we still want to be able to add up the number of cars in the first 5 miles, just based off, how dense that those numbers of cars are. I went ahead and graphed this density function right here, and we have to think about what each of the axes represent. So the x-axis is models the density of car per mile, x miles east of the city interchange. Okay, so the x-axis is modeling miles east of the city interchange. Miles east of city interchange. And then the y-axis is modeling the density of cars per mile. So this is the number on the y-axis. We'll have number of cars per mile. So say that I just wanted to find out what was happening in that first mile. So in the first mile east of the interchange, and I know that this is representing the height of my function is representing the number of cars per mile. So number of cars per mile times that, first mile, this would give me the number of cars in that first mile if I multiplied this width times this height. So this is not totally unfamiliar. We're going to sort of estimate. We'll use like a right-hand Riemann sum to estimate what was happening in that first mile. And so this point right here, just using the this guy, the function for density, I can find out that this is about 290. No, not 290 for the x. It's 1. The point is 290. And that means that in that first mile, there are about 290 cars. So one thing I do want to stress is this is like a snapshot of what's happening. These cars are not moving right now. This is a snapshot of the number of cars, at a moment, their density. So it's not like these cars are moving around at all. Okay, so that first mile, there are 290. And then I could do a similar thing where I want to find out, okay, well, what about the second mile? In the second mile, I'm one more mile further out. And in that mile, from mile 1 to mile 2, this point right here. So actually, I went ahead and found out all of these values here. But this means that between mile 1 and 2, there are 281 cars approximately. And between mile 3 and 4, there are this 1 times 274 cars. And then between miles 3 and 4, the density is about 267 cars per mile. So we know that in that mile, there was 267 cars approximately. We're missing a little bit of counting the number of cars because we're missing these areas here. But this is a fairly good approximation. And then the last one, that last mile, between miles 4 and 5, we have about 260 cars. Okay, so I add up each of these figures. This was counting the number of cars in each of the 1 mile blocks outside of, getting further and further away from the city center. This makes sense that, the density of cars is going to go down slightly as you get further away from that city center. And adding up all those cars per mile at each mile, we get approximately 1,372 cars on this road for the first 5 miles. Of course, we can do better than this because we know calculus. And so instead of taking a Riemann sum, why don't we just say, okay, why don't we count up truly the number of cars or the area under that curve from 0 to 5? That would be the integral of 200 plus 100 e to the negative 0.1x dx. And if we count up that area, it's 1393.47. So in reality, according to this density function, there are approximately 1,393 cars in the first 5 miles east of that interchange. Okay, so this is sort of a template for how we're going to explore density. And this example isn't really talking about mass, but we are counting up things. And the density of the cars, knowing that, enables us to find out how many exact cars, or over here, how many exact cars are in that stretch of road. So in that that length of road that we have, how many cars are there if all we know is the density? And this density is not continuous. This is a question that we're going to answer again and again in different contexts. So this was sort of our Riemann sum estimate, just to wrap our head around, what exactly were we counting? But then really we can get the exact integral answer of how many cars there are. Okay, now we're going to generalize what we were just talking about. So for an object of constant cross-sectional area, and this phrase constant cross-sectional area is just a condition that we're going to use to sort of simplify things in the beginning. So for an object of constant cross-sectional area whose mass is distributed along a single axis, So this is another condition that sort of simplifies things in the beginning for us. So we have an object of constant cross-sectional area whose mass is distributed along a single axis, and that mass is distributed according to a certain density function. So according to the function rho of x. So rho is a Greek letter. It looks like a P, but it's the Greek letter rho. And so this is the Greek letter rho. Whenever we see that, it's a tip-off that we're talking about density, because this is a variable that's often used for density. Okay, let's get back to what we were saying. We're setting everything up. Constant cross-sectional area, mass is distributed along a single axis according to this density function. Then, so this is sort of that's all the setup. Then we say the mass of the object between 2 points, a starting point and a stopping point. So between x equals a and x equals b is, and now here's the awesome formula, mass will be, we're going to sum up all the densities. Remember that mass equals density times volume. So the densities times the volume. For right now, we're just going to be thinking about this as the volume. This is the density. Density times volume equals mass. But we have a continual stream of these. And so we're going to take the integral from a to b. And this is the relationship that is going to help us out. So this is the formula that will help us through a lot of problems in this section. When we want to count up the mass, but we only know the density, we can integrate that density function over an interval, and that will give us the mass over that interval. So we'll say that rho of x, just remember that rho of x, is what we're calling a density function. And its units will be, so the units on this will always be units of mass over units of length. For our examples, for example, you'll have grams per centimeter, grams per foot could be one, kilograms per mile, kilograms per meter. So these are just examples here. Okay, let's look at an example of where we might use this. Okay, so let's look at this example here. Find the mass, find the mass of a 10 centimeter thin rod with constant cross-sectional area of 1 centimeter squared and a density function of rho of x equals 2e to the negative 0.2x, where x is distance from the left end of the rod and units of rho of x are grams per centimeter. Okay, so we're looking for a mass here, and we've got a thin rod, so let's draw what's happening here. We have a very thin rod and the cross-sectional area. So a constant cross-sectional area of 1 centimeter squared. This is given to us basically to consider the most simple case. Like we're just going to consider that each cross-sectional area is 1 centimeter squared. We'll revisit this, like what happens if it's not, 1 centimeter squared. But for now, we're going to find the mass. And we know that we were told before that mass is the integral from a to b of a density function dx, and so we do have a density function. What's happening here? Well, let's take a look at what this density function here even looks like. I'm interested in seeing how the density is distributed on this rod. So this density function right here, rho of x, looks like this. And on our x-axis, we have, this is measured in centimeters from the left end of the rod, and then the vertical axis is measuring density in grams per centimeter. So this is density in grams per centimeter. We can see that at the left end of the rod, the density is higher. So you can think of more mass being packed into this volume of the rod than over here. The density is smaller. So on this end, more mass per centimeter, and then on this end, less mass per centimeter. We're interested in just knowing what the total mass of this whole 10 centimeter rod is, and all we have is the density function, but we also know this relationship here. So pretty quickly we can find out that the mass of this rod is, let's see, we're going from 0 to 10, of the function 2e to the negative 0.2x dx. This integration, definitely we could do it by hand with a U substitution, but we'll just use Desmos to calculate this for us. And the solution is 8.65 And we have to think about what the units would be of this. Well, it's mass, and we're going from grams per centimeters, essentially multiplied by centimeters, so the resulting units will be grams. So this rod is 8.65 grams. Knowing a density function can lead us to what the mass of an object is. This is a continual density function. The density changes continually from the left end to the right end. The density is getting smaller and smaller. Okay, the next question I want to, well, before we answer any more questions, one little note that I want to make is this. Do you guys remember when we had velocity functions? So just remember when we had velocity functions, like miles per hour, feet per second, when we had velocity functions and we wanted to know distance, we would take the integral of that velocity function from a starting and stopping point, and this would give us the distance traveled. This is a very parallel situation where we have a certain rate and we're trying to count up over an interval, in this case mass, knowing just what grams per that mass, or the mass per volume is as we go along, and it's continually changing. It's changing at every instant. This is like when we had velocities that were always changing, but we still wanted to count the distance traveled. Here we have densities that are changing continually, but we still want to be able to count the mass of this object. And so I'll just say that when you integrate density to get mass, this is similar to what we were doing with volume and distance. It's a different application, but this just shows the power of calculus. I mean, here we're able to answer some pretty important questions, and here we're able to answer some completely different but pretty important questions as well. Okay, we've answered this question about finding the mass. We'll call that question A. And now I want to answer a different question, but still related to this situation. How long would the rod need to be to have a mass of 11 grams? So how long would this rod need to be if it had the same density function throughout? How long would this rod need to be to have a mass of 11 grams? So right now we know that a 10 centimeter rod with this density happening through the rod is going to be 8.65 grams. So we want to keep this density function, but we want a rod that will be in the end 11 grams. How long does it need to be? Well, it definitely needs to be longer than 10 because 10 centimeters only got us this much mass. So we need a little bit more, but we want to know exactly how much longer. And so essentially the question that we're asking is, we want a mass, and mass is from 0 to, we don't know the stopping point right now, so we're going to call it A of this density function. We want all of that to equal 11. And so our job really is to find the stopping point, finding A. And we'll do a method that we've seen before where we're going to actually define a new function, and it's going to be this integral with a stopping point of x, and when does, we'll define it g of x equals the integral of 0 to x and of this density function, and we want to find out when is that function equal to 11. So I'm going to define a new function, g of x, and it's the integral from 0 to x of 2e negative 0.2. X is already doing a job right here, so we need to use a different variable, and we'll use t dt. And we ask for which x does g of x equal 11. That's not too hard of a question to answer. We're going to define this function in Desmos, and then we'll find out when does that function achieve the value of 11. Hopefully that logic makes sense to you. If not, think through why am I even defining this new function? Well, this is the function that's counting up mass from 0 to a stopping point x, and we want to know when is that stopping point going to be 11. Okay, so I'm going to hop over to Desmos and define this new function. G of x is the integral from 0 to x, not 1, to x of 2 times e to the negative 0.2, and we'll use t dt. Okay, so this is counting up that mass. So right about here, right when the rod is, if we look at this point right here, right about when the rod is 2.58 centimeters long, the mass of the object will be 4.03. And we can keep going. And one thing we know is that when it was 10, which we did just a minute ago, when it was 10, the mass was about 8.65. And so that's good. But we want the mass to be 11. So how far do we have to go? Well, I'm just going to type in the line y equals 11 and see where they intersect. Oh, whoa. It's way far out there, isn't it? In fact, this density function, it gets so low that it will never reach 11 grams. Okay, so that's what we're going to answer, is that it actually will never reach it. The density function is going down so quickly that it never reaches it. So that answer here is it never does. You could have an infinitely long, thin rod, and because this density function is decreasing exponentially so quickly, it's never going to be able to add up to 11 grams. So let's answer a different question. Let's say, when is it going to be? So we'll say question C, how about the mass equals, let's just try to get to 9 grams. So this one, it never does because density is decreasing too quickly. But I think we should be able to answer this one. So let's go back to Desmos. We're back on Desmos. Let's find out when the mass will equal 9. Okay, that's definitely doable. It looks like it's right here. When the rod is 11.5 centimeters long, then the mass of the rod will be 9 grams. Okay, when the length is, I think it was 11.5 centimeters, mass is 9 grams. Okay, so we've answered a few questions. We were given a setup and we wanted to know just what the mass was based on the density. Then we kind of toyed around with the idea, well, what if I wanted a certain mass? You know, could I find the length of a rod with this density, what it would have to be? We found out that to get a mass of 11 grams will never happen. It's just the density goes down too quickly. But we were able to find out if we wanted a rod that was 9 grams, it would have to be 11.5 centimeters with this density. There's one last question I want to ask, and it is this. So the original 10 centimeter rod that we started with, where would you, so say that you wanted to balance it, and where along this line would you hold, would you put a fulcrum so that you can balance this rod? So where would a fulcrum go? Or where would you, put your finger to balance it? Where would a fulcrum go to balance this rod? And so there's, a few different, let's take 3 scenarios of this 10 centimeter rod. Are you going to balance it? We'll call them A, B, and C. Should we put the fulcrum right in the middle of this rod to balance it from left to right? Should we put it maybe over here a little bit to balance it? Would we put it over here a little bit to balance it? Well, A is not going to work because it's heavier over here. There's more mass over here. If you held it right in the middle, it would just, this part would just flop down. So the question is, do we hold it over here or is the fulcrum put over here? And definitely the fulcrum needs to be put over here. So I guess the answer looks something like C. If you were truly trying to balance this rod, the fulcrum needs to be over here somewhere. And this is called the center of mass. And so this is the next big idea that we're going to talk about. So the answer here is, we'll say C, of course. We kind of already intuitively know this. Just based on our own life experience, each of us knows that the fulcrum needs to go there. And this is the idea of center of mass. And even before we get to the idea of center of mass, which is a big idea, we first need to talk about an idea called point masses. So this will be a big idea, just as finding the mass of an object was a big idea, finding its center of mass, where it would balance, is a pretty big idea. To the idea of center of mass or even point masses, let's talk about the idea of weighted averages. Say that this was a class schedule and the grades for a certain student, a certain college student. In chemistry, they get a B+, calculus A-, history B-, psychology B-. But each of these classes is weighted differently as far as how many credits you get. Like chemistry is a 5-credit class, calculus is a 4-credit class. So we need to think about how would we calculate the GPA. Well, if, and that's a big if, all of the classes were the same number of credit hours, we would just take an average, right? Then the GPA would just be, so this is pretty standard. For a B+, you get 3.3. For an A-, you get 3.7. This is based off of a 4.0 scale. For an A, you'd get a 4.0. A B-, you'd get 2.7. B-, 2.7. So if these were all weighted of the same number of credit hours, we would just take as the GPA the average of those numbers, 3.3 plus 3.7 plus 2.7 plus 2.7, and divide by the number that there were. There's 4 of them. And this would equal, if you add all those up and divide by 4, then this equals 3.1. And that would be your average GPA. But they are not the same number of credits, and so we have to take a weighted average. So we say they are not the same number of credit hours. So we take a weighted average where we take into account, how heavy or how important, not important, but how much weight does each class have. And so the GPA actually equals, we get a 3.3 times 5 credit hours, plus a 3.7 times 4 credit hours, plus a 2.7 times 3 credit hours, plus a 2.7 times 3 credit hours. So in some ways you can tell that it was actually better to get these better grades with the higher number of credit hour classes. And so then we have to decide, what do we divide by? Do we divide by 4 still because there's 4 classes? No, you have to divide by the number of credits that there are, because each of these is being counted in our total. So then we take 5 plus 4 plus 3 plus 3. And if we do this calculation, the GPA is actually 3.167. So this is the true GPA based on the weight of each of the classes. Before we were counting it as just 3.1, we just took a straight average of these 4 numbers, but that's not accurate. We have to take into account how much weight each one was given. So now we're going to think about weighted averages and physical systems. So say that you had a bookshelf, and this will be example 4. So you have a bookshelf and you have 4 books on this shelf. At the first position, we'll call it x1 equals 0. We have a book that is 2 pounds. And then at the position x2 equals 2, we have a book that is actually 3 pounds. And we have 2 more books. One is at position x3, which is 4, maybe it's like 4, I don't know, inches, 4 centimeters. This book is kind of skinny. It's only 1 pound. And the last book is at position x4, which is 6 units away from the beginning, and this book also is only 1 pound. Okay, so we want to take a weighted average, which would sort of tell us where on the bookshelf would be the balancing point. So that's what a weighted average is going to do in this case. We have definitely some heavier books over here and some lighter books over here. So we would sort of expect the fulcrum, or the center of mass is what we're really going to start calling it, to be over here somewhere. But we want to find out exactly where that happens. So we ask, where's the balancing point? And we call this point X bar. So it has a little bar on top of it. This is the center of mass, the balancing point of this bookshelf. And we're going to take a weighted average. So X bar will equal position 0 has a 2 pound book on it, position 2 has a 3 pound book on it, and position 4 has a 1 pound book on it, and position 6 has a 1 pound book on it. And then we think about what we are going to divide by. We're going to divide by the total masses. So just up here, we divide by the total number of credit hours. Here we're going to divide by the total number of the total mass of all the books together. So 2 plus 3 plus 1 plus 1. And we find out that X bar is 2.286. So right about here is the balancing point for this bookshelf. So this is X bar, which is we'll say 2.3. About 2.3 is our balancing point. If this bookshelf is 6 units long and everything was evenly distributed, it would be right at x equals 3, but it's not. There's heavier things over here. What if we scooched over one of these books? Like, what if we moved this book over? Let's see what happens in that case. Okay, this time we have a bookshelf. I'm going to take off that this was the center of mass, and we're actually going to move this book over, say it's 5 units away from the left side. So instead of being at position 4, it's at position 5. How does that change the center of mass? Well, we think about where we think that center of mass should go. Definitely shouldn't stay where it is, but does it go right or does it go left? We'll go ahead and do the calculation, and you probably have a hunch just based on what you know about center of mass. So will X bar move right or left? Left or right? And so now X bar is almost the same, 0 times 2 plus 2 times 3, but now we have 5 times 1 plus 6 times 1 all over that same denominator of 7. And here x bar is probably what you suspected. We're getting a larger numerator now that we've moved the position to 5. And so we would expect that center of mass to move to the right. This is just like when you're on a seesaw and you want a little more leverage, you move further out on the seesaw. So x bar now is 2.43. So now the fulcrum is just a little bit more to the right. X bar equals 2.43. And you could play around with, changing some of these masses. How would that change things? It definitely is going to move this guy around, but it's all based on this sort of weighted average of this physical system. So we're now going to generalize our bookshelf example, the center of mass when you have a point masses. So this just means that you have some discrete, we had 4 books in the last example. It's not like a continuous rod where the density is changing continually throughout the rod. It's more like a bookshelf where you have these finite number of objects, so point masses. Okay, here's how you find the center of mass. For a collection of masses distributed along a single axis, the center of mass is this x bar, and it's always going to be the mass times the position plus the next mass times its position plus all the way until you've counted all of them. And we always divide that by each mass added together, or the total mass of all of the objects together, all of those finite objects. I will tell you that this expression, when you have, so we'll say a note, mi times xi, this has a name in physics. It's called the moment of the mass, mi. So if you see that word, the moment, it's the mass times the position of that certain mass. So then we want to explore moving from these point masses to when density is distributed continuously. So moving from point masses, these books on a shelf, to density distributed continuously. And this is more like a rod where the density is always changing. Okay, so we looked at an example of a bookshelf, these discrete masses at certain locations. We can find, where is the fulcrum of that, where is the center of mass. And now we're moving on to a thin bar that has density, throughout the whole bar continuously. So here the density varies continuously. And this is a slightly different problem because you don't have discrete densities and masses, but we're going to take what we knew about this and just extend it using calculus to this sort of continuous, where we still want to find x bar. So we still want to find x bar. And so we think about this thin rod or bar, and we sort of pretend that we're looking at just some discrete, we'll chop it up into some discrete areas and estimate the density for each, or estimate the mass, for each one. So here the mass on this little section of the rod is going to be that width of delta x times the density at a certain point, maybe in that region. So there's some density in here. We'll just pick one of them and multiply it by the delta x, and we'll say for this little section of the rod, we're just going to estimate the density, estimate the mass using this right here. It's not an exact because even within this little section the density is going to vary, but we'll take it as a pretty close estimate if we can take a small chunk. And so we just take smaller and smaller chunks, similar to how we've always been doing in calculus, is we estimate with a certain number of chunks and get a rough estimate, but then we take this number of chunks to infinity, and that will give us the precise answer. So here we are, we're going to say x bar is just going to be the, remembering up here, x bar was always, when we had a finite number, it was always just the mass times the position. And so here we'll say x bar is going to be the mass, or delta x rho xi. This is the density function for some part of this little tiny section, but then we need to multiply that by the position, which is x1. And we do the same thing for, say we had 100 of these and we add them together. So again, delta x rho, actually let's change this to 1 here. Our first one, our second one, and we'll keep doing it. So delta x rho of xn times the position. And then our density function that our center of mass function that we were using before, we always took this over the sum of all the masses. So here this would be, and the mass is delta x rho x1 plus delta x rho x2 plus all the way to rho xn. So we're just extending this discrete formula for center of mass, and we're pretending that this continuous bar is just a summation of some discrete elements, and then we take that delta x really smaller and smaller and smaller, so the number of these goes to infinity, and that's going to give us the center of mass for this bar where the density is varying continuously. So you could say x bar is just, if we wanted to write this as using summation notation, so nothing's really changed yet. I am going to move a few things around so it makes more sense. So we have, we're going to add up the xi's times delta x rho xi. That's on the top. And then on the bottom, we have another summation from 1 to n of just the masses. And then we let n go to infinity. And as we do, we can start introducing all of this as an integral instead of a finite sum. And so we get that x bar, in this case, this continuous density function, is going to be the integral from a to b of x rho x dx all over the integral from a to b of rho x dx. This bottom is counting up the mass of the bar, and then this is really summing up in an infinite way all of those moments of this bar, and that is going to be what gives us the center of mass. So this gives us the power to, if we have a certain density function on a thin bar, to always find where that fulcrum would be. And okay, so the center of mass for a continuous mass distribution, just meaning we don't have these finite elements, we've got a continuous mass distribution. This is the formula for center of mass that we're going to use. This is simulating a thin bar of density rho x distributed continuously from A to B. So this is a pretty big deal right here. This is going to give us the center of mass for those bars. Okay, so this is the example we're going to look at. A thin bar is 5 centimeters long. Its density is distributed according to the function rho of x equals 15x squared grams per centimeters. And we're given two jobs to do. We're asked to find the mass of the bar, so find the total mass. And we're asked to find the center of mass. So find x bar. Okay, so thinking about this density is actually increasing quite a bit, 15 times x squared. Okay, so I was just looking at the rho function here and thinking of this 5 centimeter long bar, and this is really getting heavy as you move left to right. The density is really increasing, so the mass, per that location is really increasing. So you can think of over here as like feather light, and as you move continuously over, this is becoming heavier, like rocks and boulders, and so heavy, all packed into the same volume. But we know that the mass will equal from 0 to 5 that rho function 15x squared. And so the mass of this 5 centimeter long bar, we could do it on Desmos, or we can just do it by hand. This is 5x cubed evaluated from 0 to 5. So yeah, that's a pretty big mass. So 5 to the 4th, which is, let's see, 625. So 625 grams. That is the mass of that 5 centimeter long bar, which is, as we go from left to right, is really increasing in density. So we can start thinking, before we even answer B, we can start thinking where we think the center of mass should be. It's definitely not going to be in the middle, because it's not, the mass is not evenly distributed left and right. So we think, should it be right here? Should it be right here? Should it be right here? How close? I think we all realize it's going to be over on the right side, but the question is how close to the end? Is it at the very end? Is it, more like maybe 80% of the way? So this is what we want to do next, is find the center of mass of this bar. Here we know that in this situation, x bar is going to be the integral from 0 to 5 of x times rho of x dx over the integral from 0 to 5. Well, we don't even really need to calculate this. We already calculated this guy, which is the total mass, which is 625 grams. So this is going to be the integral from 0 to 5 of 15x to the third dx. We'll just take the 1 over 625. So before we even calculate, think about what you think this number should start with. Should it start with a 3, a 4, a 2.9 maybe? Where is this center of mass on the bar? Should it start with a 3 or a 4? I'm going to go ahead and let Desmos calculate this for me. And I find out that this center of mass is 3.75. That's totally reasonable because as we move left to right, this bar is really getting, more and more dense. So we would expect it to be pretty close to 4. That 3.75, this sounds like a reasonable center of mass. Last example I want to go through is one where the cross-sectional area is not equal to 1. We've been using all these long skinny bars where we kind of assume that the cross-sectional area is just 1, but we're going to take it a little step further and say, well, what happens if that area is not 1? We need to think about what would happen in that case. Okay, in this example, we're going to look at the air density. H meters above the Earth's surface is given by some function, f of h, kilograms per cubic meter. Find the mass of a cylindrical column of air 2 meters in diameter and 25 kilometers high. That's pretty high, so that's a super high column of air with the base on the surface of the Earth. And we know that this is this density function here. So we're looking at a column of air, and this column of air goes super duper high. It goes 25 kilometers in the air. And we have let's see, 2 meters in diameter. So the radius is 1. So we think of kind of like a little slice of this column will have dh, so a change in height, and then the area is pi r squared. So here the area is pi r squared, and in this case it's just pi times 1 squared. So the area of each little disk is pi. So in this case, mass is going to be the density function, so f of h, times the area of each of those little cross sections, which is pi dh, and we're going from a height of 0 to a height of 25. Now 25 kilometers, meters, what? So it was given in 25 kilometers, but our radius is given in meters, so we're going to transfer everything to meters, so 25,000 meters. Okay, so this should count the mass of this object. Whoops, didn't mean to do that. The mass of this column of air, because we know the density function, and density is always mass over volume, then the mass equals density times volume. We have a density right here. So this is representing our density. And here we're going to count our volume of each little slice. In the past, all of the examples we've looked at so far have just had a little slice with area 1. We made it simple so that we could concentrate on what was going on with the density function. But now we are extending it a little bit where this area of the little slice is not 1, and in this case it's pi r squared, or just pi because the radius was 1. So it truly still is, though, a density type times volume problem. We just have a slightly more complicated volume than the examples that we've been looking at so far. But other than that, it's pretty straightforward. So the mass is going to be the integral from 0 to 25,000 of this function, and I'm just going to copy it here. This is our density function. And we'll let the pi come out front. And then we'll let Desmos calculate all of this. And once you calculate all of this out, it ends up being about 31,000. Now we have to think about what are the units on this. The mass is in kilograms, so it's in kilograms. I want to get a picture of what this looks like, so I'm going to graph this density function on Desmos. So this is the density function. I just wanted to kind of look at it close up. This is, with a height in meters. And then the density function, the density of the air. And the unit on that is in kilograms per cubic meter. So we can see that the density of the air is decreasing as you go higher and higher up. This is what it means for the air to get thinner and thinner as you increase in altitude. So let's just think through what we've been talking about. First of all, mass is equal to density times volume. That's our sort of base equation that we keep referring back to. And for a object where mass is being continuously distributed and the density is varying, then mass will equal from a to b the density function, the integral of the density function. So think of this example as like when we keep talking about these thin bars or rods. If you have a cross section that's not 1 or a little bit more complicated, the mass of that object, like that column of air we were just looking at, is the density function times the cross-sectional area of your object. The integral of that. So in other words, it's the integral from a to b of the density function times some cross-sectional area dx. And this is right here, this is counting the volume, and this is counting your density, and that's how we're getting mass from that integral. We're just adding all of those up. The other thing we looked at pretty extensively was center of mass. So for point masses, like books on a bookshelf, x bar was equal to, you just add up all of those moments, is what they're called, the position times the mass, and you divide that by the total mass. So add up all the masses. So this was a discrete distribution of things. So we'll say discrete. And then the calculus version of that is this x bar, where we have mass continuously distributed. So mass is continuously distributed like on a thin bar. And in that case, the center of mass will be the integral from a to b of x times the density function divided by the total mass, which we can calculate by the integral from a to b of the density function. And this, okay, so now we know about density, center of mass, mass, and a lot of really good applications